Okay, yes, so thank you everyone for joining us this morning. This is the Tiger Supply Chain Engagement webinar being hosted in conjunction with OPIN, Ocean Power Innovation Network. I'd like to welcome you all this morning. This is the first of a series of 6 supply chain engagement events that the Tiger project will be hosting between now and October this year. So if you'd like to register for the remaining events that'll be coming for the rest of the duration of the year, then please do go and take a look at our Tiger website, where you can find out all of the latest information on those events and their themes. The underlying idea behind these events is to sort of spark open discussions and sort of identify possible opportunities for supply chain to engage with the tidal sector. So I'm very keen for you to get in contact with any of us, should you wish. And the details you can see on the screen there. For getting in contact with Tiger is tigerproject@ore.catapult.org.uk. Just a little bit of housekeeping. I'd like to remind you that this webinar is being recorded and will be made available through the Tiger website after the live event. We will be hosting a few mini Q&A sessions during the event after each of our speaker slots. There's a Q&A function that you can use during the event to post questions to our speakers. And even if you haven't posted that question, you can upvote it if you would like to hear the answer to that. So please do feel free to use that functionality. So just a quick run through the agenda for today. So I'll do a very quick introduction to Tiger and also to the Open project. We will then go straight into lessons learned from the Maygen project. We'll have a very quick Q&A session on that one. We'll then go to Orbital Marine Power, where we'll get some insight into what Orbital Marine Power are doing and their O2 device, and also their experience from the SR2000 device. A mini Q&A session following that. Then we'll move on to Sabella and learn about the various projects that Sabella are involved in and the future supply chain engagement opportunities there. A mini Q&A session on that one, followed by our guest speaker slot from Synaptech. They'll be introducing us to some of their novel passive subsea monitoring systems. So just a very quick introduction to the Tiger project. Tiger is a £45 million project funded through ERDF via the Interreg France Channel England programme. The underlying aim of Tiger is to drive growth of the tidal stream energy in the Channel region by installing new capacity, and we want to drive innovation, new products and services through supply chain engagement. And this is one of our tools through which we are seeking to engage with potential supply chain partners and companies. You can see on the screen there, we've got the logos of all of our partners. There's 18 in total. The Offshore Renewable Energy Catapult is the lead partner. And you can see we are actually based in a regional office down in Hale in Cornwall. The dark green area is the program area, the Interreg region, which has funded the Tiger project. And you can also see we've identified the 5 tidal development sites which are being developed through Tiger. So we have Ramsey Sound off the coast of Pembrokeshire. We have the PTEC, so the Perpetual Tidal Energy Centre site off the Isle of Wight. We have the Ras Blanchard site, where we're not actually installing any devices at the site, but we're seeking to gain consent for the first sort of commercial arrays there. So we have 2 sub-projects within the Ras Blanchard site seeking to consent a total of 22 megawatts. We have the Pampol Brehat test site also, where there'll be another device being installed there, and Morbihan Gulf will be developed as well. So there's quite a lot of activity happening across the various sites, and the technologies involved are also varied. Activity happening across the various sites, and the technologies involved are also varied. Activity happening across the various sites, and the technologies involved are also varied. Across the technology, approximately 10 megawatts of installed capacity at a cost of around £300 per megawatt hour. Tiger wants to understand the cost reduction pathway. So it was identified by 200 megawatts of installed capacity. We should have at least halved that, if not more, down to sort of £140 per megawatt hour. Tiger wants to focus on how we are going to do that and to come up with the evidence of how we are going to do that, to then sort of support policy support, revenue support, both in the UK and France. So we'll do that through the various work packages within Tiger, all underpinned, of course, through tidal technology developer collaboration and knowledge sharing, again, which this event is all about. So work package 1 is those sites that I've just mentioned, where developers will either be installing technology or developing the consent for those sites. So that's our learning by doing. Our work package 2 is all about developing new services, products and systems, and we'll do that through engaging with supply chain, both existing and new. And work package 3 will pull all of the data, the information and learnings from that together in order to produce our evidence case for how the levelized cost of energy will improve. So that is Tiger. I'll now hand you over to Neil Farrington, who will give us a quick overview of the Open project.
Right. Oh, sorry, I'm just paused somehow. Right, that's more like it. And thanks, good morning to everybody. My name is Neil Farrington and I'm an innovation manager with the Offshore Renewable Energy Catapult. I'm just going to give you a quick summary this morning about the Ocean Power Innovation Network, which is one of the projects that Catapult is engaged in and has been helping Tiger to co-host this event. Just to give you a bit of a background on OPIN. So effectively, the Ocean Power Innovation Network is a 3-year Interreg funded programme, £2.6 million worth of funding to bring together collaboration. So initially looking at partners across Europe, which includes academic institutions, SMEs, larger businesses and research organisations, and really trying to bring all those businesses and different organisations together to help accelerate the sector. We're looking at a number of cross-regional and cross-sectoral projects. And obviously there's a growing interest now in the ocean energy sector and potential transfer of skills from other industries. Joining the network is free, so there's nothing to lose if you want to come and join us, find out a bit more about the project and potentially access some of the support that I'll lead on to in a minute. Who's involved in OPIN? So there's 7 key project partners from across Europe. So we have members from Scotland, Ireland, Belgium, the Netherlands, Germany and France, as well as the Catapult here in the UK. All these partners got extensive experience in the ocean energy sector. A number of us also run test and validation facilities. So there's some key understanding, learning services that can be offered to help support your businesses. Open membership has grown really, really rapidly, particularly over the last sort of 6 months to a year. So we now have 355 members from 25 different countries, which again gives you a real indication of the positive reaction to development in the ocean energy sector. And again, that has a global reach with particular interest in some of the activities like Tiger, for example, that are happening over here in Europe. Just to give you a couple of ideas on what OPIN can potentially do for you. So again, joining the project is free. We're running a number of different events. Obviously, they're taking the form of webinars at the moment. We've had recent events looking into funding, looking into standardization and certification, as well as a broader overview of the tidal sector. We also have a number of research reports and documents that are logged on the website, and people are very welcome to access if they'd like to join us. There are also two key services that Open and its partners run. So one focuses on a technology assessment process, where effectively we pull together the panel of partners, again with a really broad experience across the ocean energy sector, and work with specific businesses to understand what you're doing, where you're going, some of the challenges you may face, and look at how we can potentially help you map out a development pathway. To date, we've done assessments on a whole range of technologies, so from floating tidal to tidal fences, looking at floating solar. We also have the opportunity to break down into systems. So we've been looking at a number of components, going from linear generators to marine deflectors, so a whole range of options there. And we also potentially have the opportunity to offer support around services. So we're working with drone companies, for example, that have established technologies but are looking to access the offshore energy market. So again, we can work with you as a developer to look at where those opportunities sit, look at the unique prospective benefits your technology can provide, and again, map out a way for you to potentially access that sector. Again, a report is attached to that process, but there's also lots of contacts we can make with other companies to try and help you push on as quickly as possible. Another area where that technology assessment process is potentially useful, it also produces a document that can help support funding applications, support looking for investment, and give some external really evidence around the stage of development with your technology. We also run a project called Collaborative Innovation Projects, where again, effectively, we're looking to bring together businesses with common problems across a whole range of sectors. We are also potentially putting forward ideas ourselves as a partnership, again, to try and pull in collaboration, so that can take in a whole range of forms. We currently have a couple of innovation groups looking at mooring or anchoring, which again is common across the different ocean technologies. And we're also looking at corrosion as a common issue, but really happy for other partners to put forward ideas, try and bring businesses together, initially look at a collaboration, but that could potentially advance to a consortium as well, that may increase opportunities to access the offshore energy market. There's also some trouble support available. So again, any interest there, you've got some ideas, want to talk to the businesses, talk to us, please just get in contact. So just to finish up there, as usual, there's a whole load of ways to contact us through social media routes. We also have an email address and the website's there to access. So please get in touch if you're interested. Thanks.
Thanks for that, Neil. If you just go to the next slide, please.
Oh yeah, sorry.
Yeah, so just a very quick scene setter, as I'm conscious of time. So the theme for today is subsea cables and connectors. The reason being behind that is we've taken a quick look at the offshore wind sector, and approximately 80% of all insurance claims are related to cable failure, which is costing about 60 million euros per year. This is a clear message for the tidal sector that perhaps subsea assets are an area that we need to focus on to make sure that we maximize the learning from that. And a recent market update from G-Cube, who are a leading insurance broker, sort of announced recently that they're looking to increase premiums by approximately 15%, even if there are no sort of active or have been any active claims over the last few years. So this is clearly an area where we need to make sure we maximize our learning. Right, I'd like to hand over now to Fraser Johnson, who's Operations and Maintenance Manager for the Maygen project, and he'll run us through what they've been doing at Maygen. So Fraser, over to you.
Thanks, Taya. Hopefully you can all see the screen.
Yeah, perfect.
Excellent. Okay, so well, thank you all for your interest and thank you all for being there. I'm going to take you through the Maygen project, which is probably seen as the world's leading project, being edited currently as the only tidal array in the world. and take you then through some of the experiences that we've had in developing and building that project, and now going into the operating phase. The project itself is 6 megawatt array, £51 million, which was funded by Scottish Government through the REEF Renewable Energy Investment Fund, Highlands and Islands in the form of grants, and also from central government down in London. And we've also got some investment in debt from Crown Estates. So the project itself, in its nature, is commercial. We have debt to finance, and we have people to pay. And the Maygen team was set up really as an interface project delivery group. So in order to deliver the project, we took on the interface risk ourselves because there was no leading company or leading contractor who could manage that risk in that way. So we ended up with a lot of contracts and a lot of people involved in the project. It's located off the top of Scotland, so the Pentland Firth, in between the island of Stroma and the Scottish mainland. It's 4 turbines, 4 individual cables to an onshore substation where the converters and transformers are all housed. And then we have a single grid connection point into the local 33 kV distribution grid. To date, we've generated just over 30 gigawatt hours of electricity, which has more than doubled all of the tidal, stream and wave energy developers that have been deployed in the world to date. And we're still going, we're still generating. Project life is 25 years, and we're operating under the ROC scheme. So, as Teo said, learning through doing. Maygen is very much a pathfinder project. We are currently on our own, but we don't want to be. We want an industry. We want other technologies and tidal technologies that we can use and we can employ to generate tidal power. The project itself started back in 2008 and went into operation in 2018. Construction started September 14 and took about 3.5 years to complete. The technologies that we've got on site, we've got 2. They are similar in that they are 3-bladed horizontal axis tidal turbines. They're pretty much like a wind turbine underwater in how they operate, though the internal architecture is very different from the 2 systems. We have 3 turbines from Andritz Hydro Hammerfest, Glasgow-based company who are backed out of Austria from Andritz. That's a 1.5 megawatt unit and has been developed by Hammerfest, Strom, and then Andritz Hammerfest and so forth into the turbine that we have today. And I know that they are looking to extend that technology into a Mark II, which is 2+ megawatts. And then we have a turbine from Atlantis, a group company within CIMEC. That comes from primarily Australia, to be honest, with the A400. And then we've got the AR1000, which was deployed in EMEC, and recently decommissioning of the foundation was completed a couple of years ago. And in parallel to that, CIMEC Atlantis actually bought out marine current turbines a couple of years back now. And we've been fortunate to bring that technology, so the Seaflow 300 and also the CGen 1.2 megawatt knowledge in there now falls into the AR2000 and the AR3500, which are the extensions of the turbine we currently have, which is 1.5 to 1.7 megawatts. So with Maygen being a lessons learned process and a Pathfinder project, part of our funding requirement from DEC, as was the delivery of a number of lessons learned documents, and there are 3, and then an executive summary that currently exist. And they were to be delivered during the project, so design phase, construction phase, and operations. I know this presentation will go out as a PDF, so if you can download the PDF, those images will take you to the websites where those documents can be extracted. So a lot of the information I'm going to talk about here are actually in those documents in a lot more detail, but I'll take you through it at high level in the next couple of slides. So to look primarily at cable installation and connectors, Teo mentioned on offshore wind, and we certainly experienced the uplift in premiums for our underwriters, certainly in the last 6 months. We are compared to offshore wind by risk engineers, and probably incorrectly. We are we lay cables on the seabed, which is similar to offshore wind, and that's pretty much where it stops. We have an exposed seabed, we have rock, we have no sediment, we have no chance of burying our cables into sediment. That's just not there. Our flows can be up to 10 knots. We have 10-meter waves. So the environment that we operate our cables in is quite different. Some of the challenges are similar, but the design premise is the route engineering is quite different. So I'm just going to take you through some of the activities that we had around cable selection, cable stability, and then installation and cable design. Our route selection for Maygen really was started as a personal process of selecting from the bathymetry where is the best cable route that we can use. And it was really picking up the survey and following from the onshore site to the offshore locations what looks good. And that was primarily how we selected the initial cable routes. From that, we engaged with a contractor to do some CFD modeling of the site using the flows that we had and using the cable sizes that we had. So the cable diameter is about 112, 116 millimeters in diameter, which when we looked at the bathymetry was smaller or equal to the size of the seabed features that we were running through. So to try and model that in normal way and to understand what the flow would be in that really close boundary layer was quite challenging. So the CFD work was done on a number of slices across the cable, and then information was put to that with regards to drag and lift, and then we worked out whether the cable would move. Primarily, it showed the cable would move, but digging into the science behind it, we didn't think the science was accurate or giving the full story. So we chose to go a slightly different path. So instead of covering the cable in rock bags along its entire length to provide protection, we chose a slightly different route, which was to go for a cable that was very heavy. So we've got a quad armored cable. The two inner cores are for cable protection, and then the two outer layers of armor are really just there for weight, mass per meter. Make it as heavy as you possibly can. We did look at ways of stabilizing the cable and primarily found that there were no cable stability measures that would operate or work in our environment. Rock bags are okay. They're okay in groups, but they do move individually, certainly around the site in the larger waves. On the installation, we were aiming to put the cables into the natural features that we could find on the seabed. There are some quite large channels, gullies, call them what you will, that run north-south across our site, and we wanted to place the cable in those. However, the marine contractor at the time didn't have a means or technology to really aim the cable into those locations. So top picture on the left, you can see one of the cables is actually led through a fairly nice channel. It's not pronounced, but it's there. On the right-hand side, the picture, that cable is actually running along the top of a cliff. To the left-hand side is a 3-meter drop-off. If we'd have moved the cable half a meter to the left, it would have been well protected within the seabed. But unfortunately, we missed that just in process. So we were using the Coda Octopus, which as itself worked flawlessly. Unfortunately, it just really wasn't the right piece of technology for our site because of the reflection you get off the rock. So we know we want to do something better, and we know there are things out there that could do better. When we deploy cables offshore with the turbines, we actually microsite them with USBLs attached to the cables, and we go back and recover those USBLs later. So to really microsite into where we want to get the equipment. Post-installation, we did some work with University of Western Australia, who have been active in this area with cable stability on rocky seabeds for quite some time. And we gave them a lot of information and gave them a lot of data from our site. And they ran their analysis and ran their methodologies. And we found out that actually our choice of placing the cable directly on the seabed and using the features of the seabed to keep it stable was correct. And largely the cable would be stable. And then we would probably find some small areas, localized areas, where we would need to individually rock bag, but we wouldn't be doing the entire length of the cables, which are around 2 kilometers long. So just from that experience and learning, supply chain opportunities, we want to find a way of hiding our cables in and amongst the bathymetry on the seabed. It's a rocky seabed, and those features exist, but it's finding them, working out how to do that, which goes all the way back to survey data. There is an industry standard being developed for installation of cables on rocky seabeds. That needs to come and that needs to be completed. We need to get a better ability to deploy cables accurately. plus minus half a meter would be ideal. 1 would probably be okay. And a means of touchdown monitoring. We want to know where the cable's going. And we tried to do that with Coda Octopus, didn't really work, not for the technology. But there is something out there called Cablefish, which was developed primarily for this, and it attaches to the cable and sits at the bottom of the touchdown point, and you've got cameras, USBL, you know what's going on down there, and you can use that as you move forward. So I think there are opportunities there, but it is for the supply chain to kind of engage and go, okay, this is what you really need, we'll make it happen. Moving on to connectors, we have 2 types. We have a turbine with a dry mate and a turbine with a wet mate. Within the contracts for supply, it wasn't specified which was required. So we allowed the turbine developers to provide which one they thought was most appropriate. Whilst in CapEx, a dry mate may be a good idea, and it may be seen as being a low risk option. We have since discovered and shown and demonstrated that actually a dry mate connector will cost us around £3.5 million more in OPEX per the design life of the project than a wet mate. So we've got 3 turbines, 3.5 million. So one of the activities we're doing, we will be retrofitting wet mates to our dry mate turbines because of, primarily for cost, but also with a wet mate system, we don't have to operate in NEEPs. So we can play the spot market for vessels. And we have around 300 days of the year where we can install a wet mate turbine. Where we have a dry mate, we are limited to NEEP tides, and we can only use about 80 days of that year. It's about 5 days, 7 days a month, which isn't ideal. Restricts our operations and restricts CapEx, or it increases CapEx because we can only do certain things at certain times. Going on to the wet mate, it is a fit and forget solution. Once you've installed your cable on the seabed and you have a wet mate system on the end, and that wet mate is then mounted onto the foundation of the foundation for the turbine. When you recover the turbine, you don't touch the cables. The only way of really safeguarding cables is don't touch them, leave them on the seabed. If you have to move them, they need to be designed for that. But as soon as you pick them up, you run a risk. We go back to insurance claims and insurance risks there. With regards to connectors, we use Gizmo with SMI. We've used Siemens and we've used Seacon. The system for connecting those wet mates was developed by Atlantis, and they have been a world leader in that activity. They very much looked at the wet mates and that marine activity and simplifying the marine activity, simplifying the time you have on site, keeping it down as much as possible. To recover a dry mate turbine takes 5 days from start to finish with vessel mobilization. For a wet mate, it's just under 2 days. Again, it's cost and CapEx. Going into the connectors, does the industry need a common connector? The answer is no. I don't think it does. But what we do need is cleverer connectors. We need to understand the mating. We have 100 matings at the moment. We want 500. If we do 10 tests on shore, we've just lost 10% of its life. We'd like to understand, we'd like to have a method of actually maintaining those wet mates in 12 hours, not having to send them back to supplier to 4 to 6 weeks of upload. So I think overall there is engagement there that can be done, and the things we'd like to do, and it's really around simplifying costs and keeping our OPEX down. So taking you beyond Maygen, what happens next? Maygen is following the kind of wind path in trying to simplify the costs and simplify the activities. We want bigger rotors, we want bigger installed capacities, and we want less systems. We also believe we need active control systems to overcome higher flows and shed power and manage the fatigue life of the turbines. We are looking at installing subsea hubs on Maygen. This is one that's actually going to go in the next 6 weeks into the Maygen site. And again, it's about learning through doing and learning through demonstration. Looking further afield, global market. This was a slide that was done a couple of years now, 18 months ago now for Maygen. So Northern Scotland, Bay of Fundy, and Alderney. Alderney's coming on. Bay of Fundy is very active. South Korea, Southwest Japan, and the Philippines. We're currently active in 4 of those areas within Islamic Atlantis, all on the left, and within Japan on the right, which I'll move on to now. So SAE past and current supply activities. The turbine on the left, April 2020, was installed in Wuhan in China. The design was actually developed top left by Atlantis and provided to China, where it was built and fabricated in 18 months. It's a 500 kilowatt unit and is very similar to the Seaflow 300, which came primarily from MCT. And then on the right, you've got Goto Japan. Now, this is a 500 kilowatt demonstration unit, and it will go into Japan in Q4 of this year. Pictures at the bottom are the AR1000 foundation that was decommissioned from EMEC, sorry. That will be transported to Japan for installation. And then you've got the AR1500 there at Maygen. Now, it's not that device, but it's very similar. It's a down-rated 500 kilowatt unit using the power curves that were developed and validated at Maygen to go out to Japan as a Pathfinder project there. And then Alderney, Ras Blanchard. Samic Alliance Energy are involved with normally Hydrolien. So we've got a 12 megawatt array we're trying to develop there. 4 3 megawatt turbines, monopiles, collector cable, subsea hub, and export cable back to the onshore grid. Project duration is starting at the moment for consent, and then we're looking at financial close 2023, and then construction 24 and 25. So there is a lot of activity going on. There are things doing, and Maygen and SAE are very much looking at that project delivery phase, the array size, the array scale, especially at Maygen, where we have a consent for another 86 megawatts in power generation already, and are looking for technology and then government support to make that happen. Thank you very much for listening. Teo, I will pass back to you if I may, and look for any questions.
Yeah, thank you very much for that, Fraser. That's a really interesting bit of insight into the Maygen project and also plans for the future there. We do have a few questions that have popped up, and I think you've touched on this one, so I'll raise this question here. So it's how do you go about evaluating the technological maturity of wet mate connectors versus the dry mates for high voltage applications, and what would the needs be for the tidal sector in terms of these connectors in the future? I know you mentioned sort of that the implications on the operations and maintenance costs, and also the needs in future being to do purely with number of connections. But can you give us?
So at the moment, elements that we install to the seabed, so the subsea hub, for instance, that has a dry mate connector to the export cable. I wouldn't see that becoming a wet mate. It's operating. It would be operating at around 30 kV back to the shore, so similar to offshore wind. The moment all of the turbines come into that subsea hub at around 8.8 kV, which is the largest wet mate that we can find and we can get on the market. If we get to a point where we've got hundreds of turbines, then yes, maybe there'll be a industry lead or an industry interest in developing a connector for that and for the future. But at the moment, because we're installing turbines and we've got a France, their onshore grid's 20 kV. In the UK, it's 33. So the turbine voltages are changing as well, and we can put transformers into those subsea hubs. So I think at the moment, my perception is that we would use what's there. I don't see any need for the developing of a standalone unit. And the industry is so diverse. You've got Orbital, you've got Nova Innovation. All these technologies are operating at different capacities. So their needs all change, and their operating strategies all change. So for us, the wet mate is a solution to minimize the time offshore, get the equipment back to onshore as quickly as possible, whilst leaving all the clever stuff, the converters and those kind of things on the subshore, in the shore side substation, and anything we need to work on is kind of there.
Brilliant. Thanks, Fraser. We've got quite a few other questions, but I don't think we've got time to cover those now. What we'll do is perhaps follow up with some answers after the event and post the responses on the Tiger website in due course. So
no problem.
Thanks very much, Fraser.
Okay.
If I could now move on then to Trevor Walls, who's the engineering manager at Orbital Marine Power.
Yeah, thanks, Theo. Thanks, Fraser. Should see in presentation now. Yeah, my name is Trevor Walls, the engineering manager at Orbital Marine Power. Been with the company for 12 years. 10 of those years was spent as the electrical engineering manager. So I've been party to most of the developments as far as cables and connectors are concerned. I'm sorry, start video. Two seconds. Anyway, I'll carry on. Yeah, I've been party to most of the developments as far as connectors and cables are concerned. So yeah, today I'll go through some of the developments that we've made over the last few years and discuss a bit of the background, some of the lessons learned, and some of the reasons why our developments, our strategy has changed as we've built machines and as we've developed our learning. So Orbital Marine Power, company founded in 2002 as Scott Renewables, located up in Orkney. We've now got about 33 employees split between Orkney office and Edinburgh office. I started with the company in 2006. Prior to that, it was all small scale turbines, small test tank turbines that we're building. When I started, we built a 5th scale machine, which was a massive 10-meter machine. Had a rated capacity of about 2 or 3 kettles worth, so certainly wasn't worth grid connecting. But anyway, we tested that machine for a number of years, developed quite a lot of learning from that, a lot of useful data. We trialed quite a few different connection systems, and then based on that learning, we fed the learning into the next development of the turbine, which was a slightly bigger machine, the SR2000, 250 kilowatt machine. That was launched in 2011 at Harland & Wolff in Belfast. Again, tested that for a number of years. One of the big developments that we made as we were testing, again, was the connection system. Trialed quite a few different types of connection systems, and again, lots of good data, and the learning from that then transferred into the next machine, which was the SR2000. Again, built in Harland & Wolff in Belfast, launched in 2016. For us, an extremely successful machine. Very proud of it. It again generated quite a lot of data, lots of power too. We tested that for a number of years, and then again, any learning for that went into the next iteration of the machine, which is the current build, the current machine, the O2, currently in build in Dundee. So back to the 2000. So yeah, the world's most powerful operating tidal turbine at the time. 2 1 megawatt rotors, 2 1 megawatt nacelles. You can see that the main structure is a tubular structure. The tubular structure houses most of the active components for the turbine. It was deliberate that we kept most of the active components in the hull, because you can access the hull. Any maintenance can be done through the little hatches on top. You can put teams inside to do the maintenance. At the forward end, left-hand side, you can see the connection system where the A-frame is. Underneath, we have 2 sets of legs that suspend the nacelles. On the end of the nacelles, we've got the rotors. In this case, 16-meter rotor diameter, stall regulated blades, so no pitch system on this machine. Hopefully you can see this video here. It might be a bit jittery, but maintenance philosophy for our turbines, for the whole company, has been that the turbines should be quick and easy to install using locally available workboats, multi-cat type vessels. The initial philosophy certainly was that if there was any major maintenance required on the turbine, we would disconnect the turbine and take the turbine along to the harbour, a local harbour, for repairs. As we tested the SR2000, what we found was that the platform itself was extremely stable. It was an extremely safe platform for our teams to access for maintenance and the like. So that philosophy kind of changed. The vast majority of the maintenance was done in situ on the turbine itself. You can see there, I mean, there's a fair amount of tide running. It's nice, stable, safe to access. The boat's capable of doing it. So yeah, that kind of changed our thinking. So a bit about the performance of the 2000. Again, for us, very, very successful. Generated a decent amount of power. 7% of the electricity demand of Orkney over a week period. 450 days on the moorings and grid connected. It stood up to a reasonable amount of bad weather, 6 metre waves, maintained generation in 3 metre waves. To the statistics at the bottom, which are quite interesting, over 30 interventions without any lost time incidents, and no expensive vessels for access and maintenance. The last one in particular, the quickest time to repair was less than 45 minutes. So it just shows you, you get a fault on one of these machines, it is literally as simple as a team jumping on a boat, a fast rib or the like, getting out to the turbine, jumping inside, do the repair, get back out, switch it on, start generating. So yeah, as I mentioned, the quick disconnection and connection system, that was an initial design driver for the 2000. But again, what we found during testing was that the turbine was very safe, very stable, and it allowed manned intervention at very little risk. You could argue that taking the turbine off site to do repairs would potentially add more risk. Along with that, we can significantly increase yield by leaving the turbine on site. So smaller repair tasks can be done during slack tides. More rigorous maintenance tasks can be planned for neap tides, for example. So what that means is that the need for this unmanned quick connection and disconnection and remote quick connection and disconnection as it was designed, the need for that is lessened. We can move away from wet mate connectors, which is good in terms of reducing cost, size, complexity, and quite importantly, the voltage constraints that wet mate connectors have. You can see on the right-hand side the connection system that we had on the 2000. Fairly complex system, great fun to design, but a lot going on. Lots of sensors, lots of cameras, lots of actuation. Basically what this does is it aligns and stabs the wet mate connectors into the top of our mooring turret, turret being the combined mechanical mooring and electrical connection. So what we found is that the connection works, it's great, but we just don't need it. So moving on to the orbital machine, our current build. You can see same rated power in terms of the grid connected power, 2 megawatt, 20 meter rotor diameter, 74 meter long hull, so it's slightly longer, bigger rotors. Bigger rotors obviously important for increasing yield. If you increase the rotor diameter, then obviously you increase the loading. The best way to get the loading down is to go for variable pitch rotors. And the other one, forward and aft catenary mooring. So the SR2000 was a single point mooring, and the whole turbine yawed around the single point mooring, whereas the O2 machine is fore and aft moored and is stationary with respect to the tide. We can do that because we've got a pitch system. Your rotors can pitch 180 degrees. So as the tide comes in and goes out, then you just pitch your rotors 180 degrees to catch the tide. Again, moving away from wet mate connectors, so we're going for dry mate connectors. The connection itself is actually performed on top of the turbine, well away from the water line. It's a manual process, takes roughly 30 minutes. And in this case, we used an 11 kV export. That 11 kV export is just to match the grid voltage at EMEC. And again, because we don't have yawn, we don't need a slip ring, and we don't need a connection actuation. A bit about the supply chain. So this just describes UK companies that we've used. We've obviously used international and European companies as well. But a few interesting ones here. Liberty Steel. So the turbine itself is made from Scottish steel. Liberty located in Motherwell. Gray Fabrication did the main tube fabrication, so rolling the main tubes and doing the sort of heavy fabrication. These were then sent up to Texo, who are the main contractor, who finished off the tubes and assembled the turbine for us. A few other ones, ACMC did the blades down in Southampton, and Firen on anchors. A few other ones there too. So this is the part of the main tube where the equipment main equipment is housed. We call it the equipment section for obvious reasons. This is it coming out of paint, going into the assembly shed, ready to be outfitted. Again, equipment section within the assembly shed. Some of the secondary structure and handrails, etc., have been added here. And you can also see peeping out the end there, there's one of the equipment skids. So the equipment skids, this is all the equipment essentially that the turbine needs to generate power, all auxiliary equipment, distribution, transformers, all the rest of it. We assembled all that in Orkney, in our facility up here in Orkney. Tested the majority of it in the shed here, and then shipped it down to Dundee to be fitted inside the turbine. A bit about future developments. You might have seen recent press release saying that Black & Veatch are assisting us to do some research and development on future development. So essentially targeting certain aspects of the turbine that we can develop and engineer to reduce the overall cost. Certain things, electrical infrastructure, so looking at multiple turbine connections, either subsea or potentially floating hubs. Also things like cable anchoring and cable hang-offs and the like. So that should be quite exciting to see what comes out of that. And that's basically it. Some contact details at the bottom there, so if you want to ping me an email, or you can follow us on various social media channels. Back to Theo. Thank you.
Thanks, Trevor. That was really interesting. Particularly interested to see the changes from the SR2 2000 to the O2 device. We've got a few questions here. Well, there's one sort of less of a question, but clearly we've got two polar opposites from what we've just heard from Fred themselves, and I'm guessing that's just reflective of the two different strategies in terms of gravity-based versus floating, and the preferences for wet versus dry make connectors.
Yeah, exactly.
Yeah, and I've got a question here from Simon saying, are the individual rotors or turbines on the O2 or SR 2000 device, are you able to isolate and operate one at a time, or?
Technically we probably could, but we never do that, just from a stability point of view. If you were to operate one turbine and the other one was shut down, then you would have some pretty serious stability issues. Okay.
And then I have another question here. How did you have any lessons learnt on the dynamic cable aspects? I've seen their sort of future work was looking more at how the cable connects to the device physically, but in terms of the performance of the dynamic cable itself, did that all go to plan? Is that?
On the whole, yeah. We haven't had too many issues with cables. That's kind of why our focus at the moment is on connectors. Things like cable protection, we had issues with that, which we've developed different strategies for. Cable anchoring is a big one, because obviously we're dynamic, so we need to anchor the cable quite successfully. Initially, we used a fairly crude system that was just some mass attached to the cable. We've developed that into a better system for the O2. So there are developments in terms of dynamic cable, less so than connectors, I guess.
And I suppose you need to take into account the fact that you've changed from a single point mooring system to a 2-point, so the movements will all be different. And the stress.
They are, yeah. Not as much as maybe you would think. The cable anchor is still in the same position. It's still roughly in the mooring centre, so not too many differences, to be honest, on that side.
Okay. Great. Right, I don't think there are any more questions specific to you there, Trevor, so we'll move on, I think. So thanks very much for that.
Thank you.
Erwan, I'd like to introduce, Erwan Nicholas from Sabella. He's the engineering manager there, who'll give us an introduction to what Sabella are up to. So, Erwan, over to you, please.
Yes, good morning to everyone. I will share my screen. Yeah, so I'm innovation manager at Sabela, and I will present you the Sabela technology, a brief presentation of the company, presentation of the Sabela tidal stream technology, our presentation and feedbacks of our D10 project, the future development needs for connectors and cables, and the made project and procurement opportunities. So Sabela has been created in 2008 with installation of a small prototype of 3-meter diameter. And next, in 2015, we installed a D10 machine with 1 megawatt peak power. We are 25 employees. Our main work is EPCI engineering, procurement, construction, and installation of tidal turbines. We have 100% owned subsidiary company in Canada, Indonesian consortium, turnover around €1 million, on a shareholding structure, about 25% of industrial, 50% of financials, 20% of founders, and 5% of management. So the Sabela tidal stream technology aim to be simple, as the environment where we work is very harsh, so that we have a horizontal axis with fixed symmetrical blades and no yaw system to avoid wearing parts as a pitch and yaw. So we have a low rotation speed, a direct drive generator with permanent magnet to avoid the need of gearbox. We have an onboard conversion chain and transformation with complete redundancy. This is the most sophisticated part of our machine, so that we use redundancy of the conversion chain to enlarge maintenance needs. We have a modular architecture to ease installation and O&M operation, and a gravity-based support structure with ballast weight. So the aim of Sabela is to develop a complete product family to adapt to the local site characteristics, a range from medium to high power device, rotor diameter depending on available water depth, and a rated power according to marine stream velocity. Main advantage is we can standardize subparts to benefit the volume economy and ease the industrialization. Can go up to 25-meter diameter, can adapt to gravity-based or monopile foundation, and having a rated power from 250 kilowatts to up to 2 megawatts. So the D10 project is a machine installed in Ocean Island in the west of France. So the peak consumption of the island is 2 megawatts, around 900 inhabitants, and 4 tidal power gensets. The Sabela project on this island consists in 3 steps. The first one is a D10 installation we will talk about just after. The first deployment in 2015 in the Frontier Passage. The characteristic of 55-meter depth, 2 kilometers off the shore, and up to 4.5 meters per second current velocity. This project was supported by the French government. We have a 1 megawatt peak power device with 10-meter diameter rotor. We deployed it in 2015 and connected to the electrical network of Ocean Island. And we operate and monitor the turbine during 12 months authorized period. So the D10 machine is yes, rotor diameter 10 meter, 1 megawatt peak power. The basement is around 20 meter large. The total height is 17 meter, and the rotation speed is between 5 to 15 RPM with a global weight of 400 tons. The first operation we made for the installation was an export cable in May 2015. The cable was installed first on the shore with cast iron shell on the beginning of the cable to protect for the next to the shore the cable, and after it's laid free, as as explained by Fraser before. We have a rocky seabed, and we just let the cable and try to optimize the position. And at the end, we have the inline termination with a wet met connector, a dry met, sorry, connector. The first installation of D10 was made all in one with a standard heavy lift vessel selected, equipped with two 450 tons cranes and maintained position with two onshore and 3 tugs. We have a precision of positioning with a small flexibility in latitude and long, and 3 degrees for orientation, for the current orientation. We will talk about that after, but we didn't make the connection to the export cable within the turbine installation operation. We come back 3 months later in September 2015 to connect the cable. So we have to retrieve the export cable, the jumper cable from the turbine, connect it on the deck of the boat, and we start to export energy to the island in September 2015. After 12 months, we retrieved the turbine because it was the end of the authorized period. For this operation, we use a specific vessel, DP vessel, with a 400 tons capacity crane capacity. And we test also the final reinstallation test to know if the system to align the turbine on the basement was correct. The feedbacks on that is that the onshore vessels are not adapted for this operation, as we have a rocky seabed. The vessel was not able to maintain her position even with 3 tugs. And we had a damage in the jumper cable. We lost the auxiliary power supply, as we have to maintain the connector on the deck and install the turbine first. We have a traction on the cable, we damage it. And also the jumper cable handling is very complex and risky because that involves several dedicated operations during the installation or recovery of the turbine, because we have to make an export cable survey first, recovery of the dry mate connector, the connection on disconnection on the vessel deck, and after that, the immersion of the connector. And we have a high risk of damaging the cable or the dry mate connector. As we see on the picture on the right, the cable is very small compared to the weight and the size of the turbine. For future development, first we have the improvement for individual turbines for the project. I would say between actually to 2026 probably. We want to use wet met connectors to connect the turbine to the export cable. With that, we have no jumper cable to manage during the turbine installation or retrieval. We made the installation and the connection at the same time, so that we have the reduction of the duration and costs of offshore operation. And with that, we also can increase the suitable weather windows. We also need to adapt the wet met to tidal needs with the connector integrating the connection of power, auxiliary supply, and optical fiber. We need wet met connector adapted to shallow water or middle depth waters, and fouling protection with vertical connection to avoid fouling when the connector is not connected. On the power cable, the inspection without human intervention is costly and complicated with ROVs on large vessels. The inspection by divers is also complicated due to the environmental condition. We have a strong current, high depth, low visibility, swell and waves. So we need integrated monitoring for continuous survey of bend radius and for damage detection on the cable, and also sealing barriers to avoid water propagation in case of damage. For the future development, the requirement for ORE, which is probably in the time 2030, we will need subsea hubs to make the interconnection between 2 to 10 turbines to export production on a single cable to the shore. The hub will contain a switch per turbine and also a transformer. We don't need a conversion inside the hub system as we yet have it inside the turbines individually, so that we can merge the power of several turbines because the frequency is stabilized and also the voltage. Regarding the export cable, we'd have to transport around 2 megawatts to 15 megawatts, 12 kilovolts to 100 kilovolts, and up to 18 fiber optics connection to monitor the turbines. For the wet met connectors, we will need one on turbine side and also another one on subsea upside, from 250 kilowatts to 2 megawatts and 6 kilowatts to 12 kilowatts, so that this yet exists. So we need to adapt to tidal needs. And dry met connector, which is a connection of export cable on the subsea hub, from 2 megawatts to 15 megawatts and 12 kilovolts to 100 kilovolts, and also up to 80 fiber optics connections. So the main projects we have at Sabela, the first one is one developed within Tiger project, which is a Morbihan Gulf development. So the step one are two DOA 250 kilowatts power turbines. We will work on the site development and innovation. The project is financed by the Interreg Channel program. It would be a pilot farm of 2 tidal turbines connected to the onshore grids and coupled to hydrogen production units, which will be developed also in the Morbihan Gulf. As a commissioning is planned for 2022, with a 1-year experimentation as part of the Tiger project, and then operation for 20 years. Integration into the energy mix of the Gulf for autonomous and carbon-free production. So the procurement opportunities within this project will be the wet met engineering and also supply for 2 turbines, and also 2 export cable of 1 kilometer long, which have to be supplied and also installed. The second step of the Morbihan Gulf project is a complete development of the Illong site with a commercial phase. So we will have 18 additional machines to make a farm of 20 tidal turbines, remaining at 250 kilowatts power unit power. Commissioning is planned for 2026 and 20 years of operation. For this program, the procurement opportunities are wet met supply for 18 machines, turbine connection cable going from turbines to the hub, 20 cables, a subsea hub for interconnection of 10 turbines, 2 subsea hubs, and an export cable of 1 kilometer long to supply also on install. For the subsea hub, we have the installation of the subsea hub, the supply, and also the design, engineering on that. For the third step, the development of the third area of the second area, sorry, of the Morbihan Gulf area, additional farm of 20 turbines, also connected to the shore, and commissioning plan for 2030. We will need for that a wet met supply for 20 additional machines, also turbine connection cables, subsea hubs, and export cable of 2 kilometers long to supply and install. The other project is the third step of Ocean Island development, which is called FAR project, with the installation of 2 tidal turbines. It's a showcase for us for the fuel-free island energy model. This project is led by IQO Energy, final step of Ocean energy transition toward a green energy mix. Deployment of 2 tidal turbines, 1 wind turbine, solar panels, and energy storage capacity. Commissioning plan in 2022 for 20-year period operation. Procurement opportunity are wet met engineering and supply. Export cable 2 kilometers long to supply and install. So the 2 tidal turbine will have a rated power of 500 kilowatts each. And other technology, wind turbine of 900 kilowatts, 500 kilowatts of innovation solar panel, and energy storage of 2 megawatt hour. So this will cover around 80% of the needs of the Ocean Island. Another prospect is Canada. From Bay of Fundy to subarctic off-grid areas, as we have a consequent tidal energy resource with a tidal range up to 21 meters, a strong marine current in Nunavik, Nunavut, British Columbia, and Nova Scotia, remote and off-grid communities on mining industry with no interconnection, up to 100% dependence on fossil fuel generator to supply energy with a growing population, and also an awareness raising of the population toward the energy transition and the impact of the greenhouse gas emission on their environment. So we are developing a project in the Bay of Fundy, the fourth project, together with the Canadian IPP Tuglik, to deploy a 4 megawatt tidal farm. The commissioning plan for 2023-2024, and the procurement opportunity are the wet met supply for 4 turbines, turbine connection cable to connect to the subsea hub, and also a subsea hub for interconnection of 4 turbines. The cable is yet installed. Thank you for your attention. If you have any question.
Hi, Owen. Yeah, thank you very much for that presentation. I wasn't aware of quite how many projects you're currently engaged with. There's a serious amount of work going on there. I guess I sort of have, well, I'd ask the audience, if you do have any questions, please do post them on the Q&A, on the Q&A section. Just push the Q&A button below and post your question there, please. I noticed you sort of mentioned you have your Sabella family of turbines, and that you'd be looking to sort of have standardized subcomponents within those. Where do you start in terms of your design? Are you focusing more on the smaller rated turbines, so the 250 kilowatt turbines looking to be installed at the Morbihan Gulf? Or do you start at a 500 kilowatt scale for the Ocean Island? And how do you manage the process of sort of standardizing those subcomponents?
Yes, the fact is we will have two families of nacelle with two sizes. One for the small power, I think from 2050 kilowatts to 500 kilowatts, and another one to 1000 to 2000 kilowatts. The fact is, D10 turbine is really similar to the one we will make for a FAR project, the 500, because actually we have the generator of a D10 turbine is able of 1 megawatt peak, but the rated power is around 5 kilowatts. And the conversion system is able of 1 megawatt, so that we have to reduce the power of the conversion system, the capability. But a FAR project is very close to tidal, D10 project. The new development consists in the smaller design. So we will change the generator and reduce the diameter of the nacelle, so that it will constitute our small power turbine, and we can change. The rotor is not so difficult to redesign, and we have a base, common base between small to medium power and another one for high power.
And thanks, Rowan. Just another sort of question around Sabella's strategy. So I see you've sort of talked there about future developments for large-scale arrays, but you've also mentioned there sort of the remote off-grid communities. Are you looking at a mixture of all of those projects, or are you going to focus on the off-grid communities first, perhaps, and then go to large-scale array, or both?
Yes, that's the idea, to go on off-grid community first, because the aim is you have small farm for that, small capacities, but I would say the cost of energy is higher on this community, and we can have a good return on investment yet on this kind of project. So that's why we want to adapt our turbine to that, because you have a lot of configuration. You can see in the Morbihan Gulf we have 22 meters depths, so it's very different to Ocean Island where we have 55, and Canada is 30 to 40. So the aim is to adapt, have a flexibility on the design to adapt to offshore grid, and next to have experimentation on that, and next to go to larger farms.
Okay, thank you, Owen. And I sort of noticed, you were quite open with the fact that there were issues in terms of installation and cable management. Is that going to be a particular area of focus for Sabella and perhaps maybe the sector as a whole going forwards, do you think?
Yes, I think so, because yes, wet met is really important for us, because the main problem is management, handling of the jumper cable during the installation, as we have several operations to do with it. But the cable we have a bend restrictor on it, but it's quite weak compared to the weight of the connector and the weight of the turbine, so that it's very difficult to manage it. And this is a crucial point for us to design a wet met connector and to adapt it to tidal.
Okay, brilliant. Thanks very much, Erwan. I think I will now move on to our next presenter, Tom Morley, who's Business Development Manager at Synaptech. I'm sure all of our developers will be interested to hear what Tom has got to say, as he'll be covering a novel sort of cable monitoring system. So if I could hand over to Tom.
Thanks very much, Theo. Hello everyone, I'm Tom Morley from Synaptech, and we develop and manufacture the world's first scalable passive electrical and mechanical sensor network, and I'm responsible for business development in the renewable sector. We're based in Glasgow, where we developed our completely passive solution for distributed electrical and mechanical sensing. We combine electrical and mechanical sensors with distributed acoustic sensing, known as DAS, to give us unprecedented visibility and control of power systems. The technology was originally developed for the subsea sector, and we have systems installed with transmission operators as well as with offshore wind. In transmission, we've installed with Scottish Power here in the UK and with Statnett in Norway, where we're instrumenting for electrical protection. And we're being installed later this year with SSE, where we're helping reduce the cost of new grid connections. In offshore wind, we have a system installed with the ORE Catapult test turbine in Leavenmouth. And we have a larger system being installed with Vattenfall later this year. At the heart of our technology is the ability to measure passively electrical and mechanical parameters at distances of 100 kilometers from the substation and synchronously timestamp, process, and publish this information in a central location. We combine the electrical and mechanical sensing with DAS to give a holistic platform looking at cables, cable terminations, and generators. The key part of the technology is the passive nature of the sensors, which mean we need to have no power, comms, or time clocks at the measurement locations. We were involved with the Clematis project, which finished in 2018, where Synaptic, the Fraunhofer Institute, and the European Marine Energy Centre in Orkney were involved in this project. The point of the project was to show how Synaptic could be combined with DAS and DTS within a single fibre. And it's this combination of technologies that gives a holistic monitoring system. Our system provides benefits over 3 distinct timescales. We combine DAS with point measurement for current, voltage, temperature, strain, and vibration. In time-critical electrical protection, we're operating in milliseconds, and we're instrumenting for electrical protection so that each section of cable can be protected. In real-time monitoring, we're providing information for dynamic line rating, cable connection temperature monitoring, as well as fault location. The asset management applications provide information on longer-term trends, and here we are looking at measuring power quality to optimize performance and help with preventative maintenance, as well as looking at cable movement to detect areas where there is increased likelihood of damage. So now we'll just look at each of these applications in a little more detail. Using our system for instrumentating a cable means you can have current differential protection rather than distance protection. Current differential protection is more reliable than distance protection because distance protection in certain circumstances will underreach or overreach, leading to misidentification of faulted sections. By instrumenting each cable in the string, if you have a fault in one cable section or on one generator, you can detect the fault and auto reclose up to and around this fault. This means if there is a fault on a generator or the generator is removed for maintenance, you're not losing the output from the whole string. For real-time monitoring, we use a combination of current and temperature sensors to allow dynamic line rating. This is possible as the sensors give instantaneous data, which allows an operator to increase and decrease the power and still stay within the operating parameters of a cable. The other area to monitor is cable terminations. In the offshore wind sector, there have been a high number of failures in these locations, and conventional monitoring systems have monitored cable temperature, but not that at the cable termination. The same sensors that are used for electrical protection can also deliver synchrophasors and power quality at every generator. This is in contrast to existing technologies which only view the aggregate data. By seeing the synchrophasors and power quality from every generator, we can display this data showing where and when events happen, as well as comparing data from multiple locations. Because we measure at every generator, the analysis of power quality across the array is much more accurate than traditional methods, as harmonic data is not lost through interaction between generators. From distributed power quality data, we can detect oscillations, compare data from different locations to give an overall picture of the performance and condition of the network of generators. And over time, analysis of outliers and deviation from the norm will help shape operation and maintenance by providing advanced warning of failure. The data from the distributed acoustic sensing detects strumming in the cable, and by analysing this strumming, we can determine sections where there's the highest risk of damage to the cable, and operators can use this data to assist with decisions on the areas for pinning. The next couple of slides give a bit more detail about our installation with ORE Catapult on their test turbine. Our project with the Catapult was in response to the cable failures which Theo has already spoken about in the offshore wind sector. Using the Synaptic platform, we have instrumented for current differential protection for the array cable, temperature sensors that monitor cable terminations, including overheating alarms, and these same sensors are also giving power quality data. These photos show the components of the installation. So in the center, we have the CTs. These are very similar to CTs, but the only connection going back to the substation is the single mode fiber, the black cable you can see between the CTs. Is also worth mentioning, we can either supply our own CTs or connect to the secondary output of existing CTs and VTs. The picture on the right shows the temperature sensors, and these are on the cable terminations, and these are sharing the same fiber with the CTs from the central picture. And finally, on the left, we have the interrogator, which is located in the substation. Here we correlate all the data and timestamp it before publishing it in the required format. We also have the option to visualize and store the data on our platform, which I'll show you on these next slides. This video shows the installation at Leavenmouth and the two locations of the sensors. So at each end of the array cable. This is to help operators quickly visualize where the data is that they're looking at. This slide shows the information from each of those locations. We can see the frequency, current, which has the amplitude and phase, as well as the temperature of each phase at the cable termination. And here we can see the raw data, and this is shown in real time. And then on the right, you have the power quality that has been analysed. All this data you've just seen can be stored and viewed, and that makes it very useful for post-event analysis. So in summary, we've invented a unique new platform for passive monitoring of remote and inaccessible HV assets over unprecedented distances, and we're bringing together electrical and mechanical point sensing with distributed acoustic sensing. We welcome input from operators and developers on any needs and requirements they have. And thanks very much to everybody, and I'll pass back to Theo.
Tom, thank you very much for that presentation. It's really interesting to see sort of cutting edge bit of technology, really, that I guess originally your focus was targeting the offshore wind sector.
Yeah, transmission for the utilities, transmission, distribution, and also offshore wind. And the offshore wind has been because it's such a growth sector, and as you alluded to, they've had quite a lot of problems with the cables and are looking for new technologies to try and reduce these failures. Okay, and it was quite interesting to hear there that you may well be developing the ability to detect cable movement through the passive system. Can you just explain a little bit how that would work? Yeah, so using DAS, which is digital acoustic sensing, you can detect cable movement. Now that's useful, but if you can go further than that and you can look at the frequency the cable's moving at and then compare that to either test data or data from the manufacturer, you can say, right, we think this area, the movement is less likely to cause concern, and this area, we think this is going to be the greatest area where damage might occur. Now this has been hasn't been proven on scale or anything like that. So this is why we're sort of keen to come to events like this and speak with developers and see if this is something that they would be interested in trialing in these projects that you're organising at Catapult.
And do you think that this system could be deployed whilst you're actually installing these cables, or would it be only once the cables have been installed?
I think there is possibilities for using the strain sensing capabilities we have for developing something when you're laying the cable. And it's something we could talk to people about, but the main thrust of the strumming is to be looking at cables once they've been installed.
And we have a question on the Q&A just saying that is the sensing utilising fibres that exist within the cable?
So for the point measurement, we use the fibre within the cable as the communication backbone, but we splice in at junction points the synaptic passive sensors. And then for the DAS, we're using the cables already, the fibre already within the cable. But it's just the normal single mode fibre. And as we spoke about with the Fraunhofer research, and that's all about using the same fibre. So if you're using your fibres for communication and control of your assets, you don't want to give away a whole lot of fibre to monitoring. So we can just use a single fibre for this.
Okay. I have another question here. Is the DAS capability provided by Synaptec, or is it supplied through a third party?
It's through a third party. We work with a number of DAS providers to offer this sort of holistic system. So
the value for Synaptec is in the
point measurement, and possibly depending on an operator's requirement, like we've developed this dashboard, which was in the videos, which is about displaying data for people and capturing that data. So there may be a possibility if people are looking to include that, of including it within that platform.
Okay, good. Thank you. Thanks very much, Tom. I think
Thanks so much.
We have a little bit of time left, so what I might do is open up the floor, if I can, to all of our speakers. So if anyone's got any questions for all of our speakers that you've heard today, feel free to post the questions on the Q&A, and we'll see if we can answer them now. So I'm going to ask our speakers just to turn their cameras on so we can see you. Hi guys. So I'm just having a quick scan through the questions. So there's one here aimed at Sabella, just asking about integrated monitoring for continuous monitoring of bend radius of the connector for damage detection in the cable. What are Sabella's plans for this? Is there anything available on the market for you to do that, or does the development of a system that Tom has just discussed of interest, do you think, to the sector? I guess I could open that up to all of you really, rather than just Erwan. Sorry, Erwan, you're on mute. There we go.
Yeah, sorry. Yes, I think this is a kind of development we need, and we know that it is under research, actually, in pre-development. The fact is, as we have harsh current, we did a survey with divers all along the cable once, but for the first, the beginning of the, how to say, the tidal farm, we will need to have a better survey on cables, as the cable are let on the rocky seabed, and we try to find the best way to maintain it, but to be sure that we have not, as we probably have free span zones, to be sure that there is no risk of damage on the cable, and to know if the frequency is changing, so that we can anticipate the failures. So the fact to anticipate is important, as we use vessels that are DP vessels, which are costly vessel, but also not so we have not so much on the market, so that if we can anticipate the operation, we can not have too much downtime due to the operation.
Thanks, Johan. Can I open that question up to Fraser or Trevor? Do you have anything?
Yeah, so I mean, certainly from our perspective, Theo, yes, very interested. Our maintenance strategy for the cables are we inspect them every year in around Q2. We go out and do a visual inspection with an observation ROV. And from that observation, from that survey, we watch the video and then we go back and identify areas where the cables are moving or have moved, or we've got some abrasion on the seabed or abrasion on the cables. In some areas, we're wearing the seabed away. In some areas, we're wearing away the armor on the outside of the cables. But yeah, getting that kind of information in real time or being able to transfer it across and get a historical knowledge of where is the cable moving. And if we are going to put stability measures in, where do I focus that effort? Where do I focus that cost? Because it all comes down to cost of how do we do this? And then the question is, can we get to a point where actually we're monitoring the cables to an extent where can we self-insure them? Can we take that out of our insurance premiums? And if we did that, what would it do to our underwriting costs? So yeah, very, very interested from a developer's perspective.
Thanks, Fraser. Trevor, do you have anything to add to that one?
Yeah, no, definitely interesting. Obviously, we're highly dynamic being a floating structure. We did a few years back have some involvement in the Clematis project, and some of the data that we got out was interesting. It was a really neat system. I think from memory at the time, we had issues getting sort of magnitudes of motions possibly at the time because it was installed in an existing system. So really useful to do right at the start of a project rather than kind of halfway through.
Okay, thanks, Trevor. Just a quick question for Tom, actually. So there's a question here, which is a good one. Can the sensors be installed by ROV? So once the cable's under the water, can you install these sensors?
I have to say I'm not sure. I'm not sure of the capabilities of ROV. But if anybody wants to contact me after this, I can certainly, we could discuss it with our engineering team and just how these sensors are connected, but I'm afraid I'm not sure.
No, that's no problem. Thanks, Tom. I got a question here, sort of an open question to all the developers. So what are your priorities for connector development? Could you each sort of summarize what your sort of key priorities are? Should we start with Fraser?
Thanks, Theo. I would say repair. So there is nervousness about using wetmates because if you do damage one, then you're going to have to send it back to Siemens or Gizmo, and it's going to take 10 weeks to repair. That's too long. We can't at the moment afford to have multiple spares just sitting around in case we do break one. So we need to find, or the suppliers need to find a way of not re-engineering, but just changing maybe what they've got so that that wetmate connector, if needed, could be repaired in a 20 foot container workshop on the back of a ship in 12 hours, not back at Siemens or Gamesa over 6 to 10 weeks. That for me is probably one of the biggest issues. We have the same problem with dry mates, don't get me wrong, but yeah, repair of a potential fault is probably one of the key areas of concern.
Okay, can I pass that question then to Erwan? What's Sabella's priorities in that area?
Yeah, I think Fraser resumed well in his presentation what is needed for the wetmate connectors. As we are in a specific environment, and all the wetmate connector we will use in the future are adapted for offshore oil and gas, so that we have different depths of water, only 50 to maximum 100 meters, not 3,000. And also we have a shallow to medium water, so we have the problem of fouling, and for example the need to have protection without putting a specific protection when the connector is not connected is important, because this is during the operation one operation more with the ROV and the DP vessel. So all of that are very need specific to tidal, I think, and this is what we want to work on for the next steps.
Can I just add to something there, Theo? as Erwan's just mentioned, within the Atlantis wetmate system, we have a cover that we have to place over the wetmate. So we recover the turbine, get it out of the way, and then we have a cover we replace over the wetmates just to make sure, as Erwan said, that we don't get fouling or we don't get any grit or any sand and that kind of suspended sediment into the wetmate onto the face. If we could have a system that was automatically covered, that's something that we have in development ourselves. If that can come from a third supplier, from a supplier of the wetmate, brilliant. Yeah, that would be of use.
Trevor, you got anything to add to that one?
No, I mean, I would second what Fraser and Erwin say about wetmates. We had exactly the same issues, and if we were to go back to a turret type mooring, we will still have the same issues. The development of the dry mate changes things slightly because the dry mate's on top of the turbine. We can access it and we can maintain it, and potentially we can resplice it in situ. So it's got slightly different benefits, I guess. So yeah, just making the system simpler and cheaper is the main priority.
Okay, I got an interesting question here. So, as Trevor, whilst you're there, I guess, do you think that consolidating the technical demand would give access to greater volume and would accelerate development and drive economy of volume for these connectors? Is there an argument to be made that you, as technology developers, should to some extent be working together and creating a volume requirement for the market to supply?
I think it's a difficult one because, as I've said, our requirements are divergent slightly. If you'd asked me 5 years ago, yeah, I would have said exactly that developers should be working together to develop a system that works for everybody, because all our requirements would have been the same, but things have changed. So yes and no is the answer.
Yeah, just to give that an analogy, I mean, the orbital system and the systems at Maygen are similar in the fact that they are fixed to the seabed, just in different ways. They are horizontal axis turbines, just have different number of blades. I suppose if you look at fixed offshore wind and look at floating offshore wind, they are the same, but very different. And I think that's where you come to the orbital device and you know, the more traditional seabed fixed devices. They are the same device, but actually their operation, the philosophy of the operation is very different, and therefore the requirements can be very different. Neither one is better than the other, but they are working in the same environment. So I think there's market for both, and unfortunately they are just going to be slightly different, the same as floating and fixed offshore wind.
Erwan, do you have anything to add to that? Do you agree?
Yes, I agree with both. I think we have some difference between floating and gravity-based turbine. And I think the system operated by Atlantis is what we aim to install also in on Sabella side, as we have probably specificity to, for example, for the alignment on the turbine on the system, but the requirement on the connector himself would be probably the same. So we have to discuss between us, and we managed to initiate a discussion on that. And I think it's the aim also of Tiger to all the points that are not in the core business of the tidal developer need to be. We need to have a, how to say, to merge just the specification to have a more global market, and to not to have a sort of standard by developer.
Okay, just a sort of a general question. So do we think that there's been progress in terms of convergence in the design? I know we've got the two different concepts of floating versus gravity-based, but are there any elements in terms of the design that are now converging? You know, for example, are all gravity-based devices now thinking, well, we must go for wetmate? Does anyone have an opinion on that? Do you think there is an element of convergence?
I think the convergence is, if you pick up your turbine and you want to take it back ashore on the deck of a ship to maintain, you want to spend as least time as possible on site with that very expensive asset. So you pick it up as quickly as possible and you go home. taking the orbital route where you are planning to stay on site and do your maintenance on site, it's a different requirement. They have a different philosophy. So there is a convergence there will be a convergence from seabed mounted, even if it's HydroQuest, which is a very different turbine. If they want to recover the turbine, you still want to disconnect it very quickly. For us, we don't want dynamic cables. They are different cables. You have to put a connection in. They cost difference. They are in the nature dynamic. Put the cable on seabed, leave it alone. But for design for the right purpose, all will have the right system, have an appropriate system. So, yeah, there is convergence, but I think we're going to end up with two different systems. I mean, and just to pick, locations in China where you want to install, in Wuhan, you wouldn't deploy a seabed mounted device in Wuhan without a surface piercing monopile. The water is full of sediment you cannot see. So how are you going to do all your marine operations underwater unless you're using sonar, and it's quite expensive to do that? Actually, floating would be a sensible option there. So yeah, different technology for different locations. We have more opportunities with different technologies globally.
Okay, so I guess making a comparison with offshore wind, all of the turbines look pretty much the same, so the convergence has happened. But we're sort of forecasting that with tidal, we don't expect to converge to that extent. There's going to be a few different designs on the market.
I think there's a few different foundations, support packages. So you've got seabed mounted, has a support package, floating has a support package. They're both fixed to the ground. One's got a mooring, one's got a foundation. They've both got anchors, one's using a mooring, one's using a foundation. It's just, it's horizontal axis, blades, generator, slow speed shaft, high speed shaft, call it what you will. I think it's just that's a support package which is different.
Yeah, that's exactly what I was going to say. The actual power takeoff of the machines are and probably will converge.
So does that mean the electrical components would converge as well? The cables, the connectors, etc. I suppose the cable designs. I mean, are the cable designs between the Magen project and what you guys will be using it for the O2 device, are they substantially different?
I mean, again, that we are floating, so like Fraser said, we need a dynamic cable. So that is different, cable anchor, etc. In terms of the electrical equipment on the turbine itself, it's all much the same kit. It's all the same power converter, generators, gearbox, that type of thing.
Yeah, pretty much.
Okay, right. I think we've covered the majority of the questions that have been posted by the audience. So I think it's time probably to wrap up. So if I could just thank all of the speakers for their participation today. I definitely think it's been a real interesting webinar, and there's been a nice bit of insight into what you have done in the past, but also what you're looking to do in the future. Through Tiger, we're keen to work with all of our technology developers and to stimulate that engagement with supply chain. So if there's anyone listening in who has sort of sparked a real interest in what the tidal sector are doing, and you think you may have a product or a service that may interest anyone within the sector, to be honest with you, then please do get in contact with us. I've got the contact details up on screen there. So to contact the Tiger Project, it's tigerproject@ore.catapult.org.uk, and anyone who would be interested in getting in touch with the Open Project, it's open@saai.ie. So yeah, thank you very much everyone for joining this webinar, and thanks again to all of our speakers.
Thanks, Teo.
Thanks, Teo.
Thank you. Goodbye.
Thank you. Bye-bye.
Goodbye. Thank you.
Cheers.